This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
Tonight you're going to hear 3 talks from 3 members of the Memory and Aging Center, which is actually just right across the street in Sandler Neurosciences. So first I'm going to talk about brain games that capture brain circuits, specifically how to use brain games to make inferences about memory systems. And after me, you'll hear from Bettcher. She's also a neuropsychologist at the Memory and Aging Center, as I am. And she's going to talk about the evidence for using brain games to improve your cognitive function. And lastly, you'll hear from one of our neurology fellows, Winston Chiong, who's going to talk about neuroscience and philosophy. So I think it'll be an interesting evening. So in my talk, I hope that you'll learn that there are multiple distinct memory systems in the brain. And by using carefully designed cognitive tests, we can measure separately how well each of these systems are functioning. During the first half of my talk, I'll focus on the distinction between working memory and long-term memory consolidation. I'll start with the story of a famous patient known as HM, who taught us that there are multiple memory systems in the brain. Then we'll try out some tests of working memory and long-term memory, like the ones that we use at the Memory and Aging Center. And last, I'll end with that section, I'll end with some tips about how you can maximize your memory function using these insights from neuroscience. During the second half of my talk, I'll focus on the distinction between allocentric and egocentric navigation memory strategies. So there's 2 major ways that we can navigate, how we can find our way around without getting lost. And I'll ask you, which strategy do you prefer to use? At the Memory and Aging Center, the most common reason why new patients come to us is because they have a memory problem. When a patient tells us that they have a memory problem, we ask them to give us some examples. And when we ask this question, we get very different answers. So here are some of the most common answers that we get. I have trouble finding words or names when I need them. Sometimes I can't remember why I walked into a room, especially if I get distracted on the way. I forget where I put my keys or parked my car. I can't remember the meanings of words or even what objects are used for. I sometimes forget what I did yesterday or last week, and even when I am reminded, I sometimes can't remember. These are all very different memory problems, and in fact, they rely on different memory circuits in the brain. We learned that there are different memory systems from a famous patient who is known as HM. HM had a seizure disorder that was not well treated with medications. And so his surgeon, Dr. William Scoville, performed a bilateral medial temporal lobe resection, cutting out the middle parts of his temporal lobes, including the hippocampus on each side. You can see in the figure there on the left in HM's brain, there's a big chunk of brain that's missing. So the good thing about this surgery was that it cured his seizures, but it had a horrible side effect. He could no longer commit new events to his long-term memory. He actually lived a long life, and he'd see the same doctors sometimes day after day, and it was like he was meeting them for the first time. So HM was impaired at laying down new memories, long-term memory consolidation. This is the type of memory that we often mean when we talk about memory. It's what we use when we're a student and we study a subject so that we'll remember the information later. It's memory for facts and events. It seems to have almost an unlimited capacity. One of the important findings with HM was that there were memory functions that were spared. So we know that the medial temporal lobe is critical for long-term memory consolidation from HM, but we know that it's not critical for some other memory functions. For example, HM was able to learn new skills. We call this type of memory procedural memory, like learning to dance the salsa or learning to ride a bike. It becomes a habit after a while. You don't even really have to think about it. You just remember how to do it, almost effortlessly. So this is called procedural memory, and it's subserved by a very different brain circuit than the long-term memory consolidation. Short-term memory was also relatively preserved in HM. It's also called working memory because we use this kind of information to hold small amounts of information in our mind so that we can work with the information. This type of memory is very temporary and has a very small capacity. So again, these two types of memory were preserved in HM despite the fact that he had those big chunks of his medial temporal lobe removed. So HM taught us that there are multiple distinct memory systems. So I'll talk a bit more now about this short-term or working memory. It's the type of memory you're using right now to listen to this talk and process it in your mind and think about how the stuff you're learning may apply to you or people you know. You're processing or working with this memory as you listen. So working memory holds information in conscious awareness so we can use it. The information can come from our senses, like right now, you're listening to me talk, and that information is going into your working memory. The information can also come from your long-term memory stores. The duration is seconds. It only lasts up to maybe 20 or 30 seconds, unless you keep rehearsing the information over and over again in your mind. For example, if someone said a phone number to you, and then you walked over to the phone to dial it, you would hold that phone number in your working memory so that you could remember it when you need to dial on the phone. But if someone distracts you when you're on your way to the phone, you're likely to use it. And that's because this working memory has a very limited capacity. And so distracting information can compete with the information you want to pay attention to, and then you can lose it. So it can only hold about 5 to 7 items in your mind at a time, which is perfect because phone numbers are about 7 digits long or 9 digits. If you can chunk the information, you can hold on to it longer. So, for example, if you recognize an area code in the phone number, you can chunk that and it becomes 1 unit. And then you only have to remember the other 7 digits. So the better you inhibit irrelevant information, the more information you can hold in your working memory. Now, I think this is why people who are under a lot of stress have trouble with their memory. They may have a lot of distressing thoughts that are interfering with their working memory. So there's not enough room in their working memory for what they want to pay attention to. So good strategies for improving your working memory are to reduce your stress and also just try to reduce distracting information. If you need to concentrate on something or concentrate on an important conversation, try to do it in a quiet place with fewer distractions. So let's try a working memory test now. I'm going to administer to you a very popular neuropsychological test of working memory. I'm going to say some letters and numbers to you, all jumbled up, and I want you to say them back to me with the letters in order first, followed by the numbers in order. Okay, are you ready? All right. F3A8. All right, good. Let's try a longer one now. All right. KW92P. All right, good. So that's a test of what we would call verbal working memory, where you have to hold online those letters and numbers and manipulate them, reorder them in your mind. So now let's try another test of working memory that we're using in our research right now. I want you to remember the last 3 locations that are shown. So this is a test of spatial working memory. It turns out that spatial working memory and verbal working memory, the test we just did, have some similar neural underpinnings, but also have some separate neural underpinnings. So for example, some patients might be impaired in spatial working memory, but not verbal working memory, or vice versa. In Alzheimer's disease, early on, working memory is actually pretty good. But the type of memory that they have problems with is the same type that HM had problems with, long-term memory consolidation. Why is that? Well, you can see in this healthy control brain, this is the hippocampus. It's nice and tight and plump and lots of neurons there. But in the Alzheimer's brain, there's a lot of black, which is the cerebral spinal fluid that has come in to fill in where the neurons have died. So this is an early target of Alzheimer's disease. And this is why early in the disease, many patients have trouble laying down new information into long-term memory stores. They may have trouble telling you what movie they saw last week, for example. Well, let's try a test of memory, a test of long-term consolidation. So I'm going to read a list of words to you. I want you to listen carefully, and when I'm through, I want you to say them back in your mind in any order. And if you want, you can try to keep track of how many you're remembering on your fingers or tallying, but don't write down the words, okay? So I'll read the list of words to you, and then you can repeat them back to yourself when I'm done in your mind. Arugula, paperclip, apple, stapler, telephone, gorgonzola, scissors, red onion. I'm finished. Repeat them back in your mind. Okay? Let's try it again. Let's see if you can remember more this time. It'll be the same list. Arugula, paperclip, apple, stapler, telephone, gorgonzola, scissors, red onion. Okay. We administer a test like that one to all the patients who come in our clinic. And what we find is, the first time we read the list of words, the Alzheimer's patients perform pretty similarly to controls. So this test actually, I think, has 16 words. It's a different test than the one I just gave you, but it's similar. And at trial 1, they repeat back a similar number of words. But then over the learning trials, we actually administer 5 learning trials. You can see the controls get better every time. Every time they remember more words. And this is because their hippocampus is helping them to consolidate the information. But in Alzheimer's disease, they don't show as much improvement over the learning trials because their hippocampus is not as effective at this. And importantly, over the long delay, which is 20 minutes, we see that the Alzheimer's patients remember almost none of the words, In fact, many of the patients don't remember that a list had been read to them. So this is a problem with long-term memory consolidation. How does the hippocampus consolidate new information into long-term memory stores? Well, it consolidates the memories in a widely distributed network of brain regions in neocortex. So for example, let's say you went to an important family wedding several years ago. Well, the brain doesn't just consolidate your memory of that wedding into one node in the brain and its connection to hippocampus. Rather, it consolidates the memory in a widely distributed network of brain regions, the same brain regions that you used when you processed the information at the wedding. So the same brain regions that processed the sights of the wedding and the taste of the cake, the sound of the music, the conversations that you had there, the emotions that you felt there, those same brain regions are involved in the memory for the event. Emotion in particular seems to be a really important organizing force for these memories. So these nodes in your brain that represent the event are all interconnected functionally for this memory and connected with the hippocampus. And every time you recall that wedding over the years, these same regions are active and interact. The hippocampus is critically important for bringing up that memory. Over time, however, the hippocampus becomes less and less important for bringing up that memory. So many years after the wedding, the hippocampus may not be important hardly at all for bringing up that memory. This is why patients with Alzheimer's disease can remember better events from earlier in their life than the movie they saw last week. They may be able to tell you stories from their childhood, but they can't remember that you went to a party with them last week. And this is because the hippocampus is less important for recalling memories from earlier in your life than for more recent events. So we've talked about the brain circuits important for memory and the differences between short-term memory and long-term memory consolidation. What can we take from all of this to maximize our memories? Well, I'm going to leave you with 2 tips here. The first is we remember when we pay attention. So when you focus and you reduce distractions. And the second is we remember when we make it meaningful. So when you make associations that give new information, context, or significance in terms of all the other things you have in your mind. The reason this works is because memories are stored based on their associations to other events or memories. So let's try this technique out. So Bree is someone you're going to meet in a few moments. She's going to give the next talk. And I don't know about all of you, but sometimes when someone introduces themselves to me, I hear the name, and a second later, it's gone. So I encourage you, when someone tells you their name, to stop a moment and focus and make associations. So for Brie, you might imagine a plate of Brie cheese, right? And just think about how delicious that cheese is, and imagine Brie eating that big plate of Brie cheese. You'll probably never forget her name again. And if that doesn't work, I have an even better strategy for you. Now you can think of someone else you knew by the name of Brie. Maybe there was a girl back in high school with the name of Brie. And even better, let's say that she stole your boyfriend. So you remember that girl Brie who stole your boyfriend? Well, remember, emotions are a very powerful organizing force for memories. So if you can activate your emotions while you're trying to remember something, you're much more likely to remember it. All right, let's try another one. So Winston's going to be giving a talk on philosophy and neuroscience later this evening. And I think it's going to be a really good talk. So you could remember, Winston, he's a real winner. Or you might think of Winston Churchill. Winston Churchill was always smoking cigars. So you might visualize Winston smoking a cigar. So the more you engage your different senses, I find visualization in particular to be helpful, the more likely you're going to be able to remember new information. So we've talked about short-term memory and long-term memory and how to transition information into long-term memory. And again, the tips I have for you are 1, stop and pay attention, and 2, make associations. Because we consolidate long-term memories in terms of their associations to other memories or concepts. The most effective associations are original, even absurd. They engage multiple senses, they engage emotions, or they're personally salient. So before we shift to the second half of the talk, I'll just review the brain bases of these two memory systems. So the short-term memory, or the working memory, relies principally on the frontal lobes and frontal parietal circuits. But the long-term memory consolidation relies critically on the hippocampus. And over time, the hippocampus lays down memory throughout neocortex. And after many years, the hippocampus isn't even really that critical to recall the memory. So now I'm going to move to a little talk on navigation memory. So I want you to think for a moment, how will you find your way home after this talk if your GPS isn't working? There are two primary strategies that we use to find our way around. The first that I'll talk about is the allocentric system, which means other-centered. When we use this system, we represent where locations are relative to major landmarks in three-dimensional space. We often anchor our allocentric cognitive maps in Cartesian coordinates, north, south, east, west. For example, if you are using the allocentric navigation system, you might think, my house is north of UCSF between Coit Tower and Fisherman's Wharf. So you're appreciating the relationship between these major landmarks in space. Your allocentric cognitive map of San Francisco does not change if you are at UCSF, if you're at the Golden Gate Bridge, if you're in New York City. It's the same map. It doesn't depend on your position in space. This system relies critically on the hippocampus, more so on the right hippocampus in the posterior portion. So in contrast to the allocentric system, the egocentric system is self-centered. When we use this system, we chain responses with local cues. For example, you might think, to get to my house, I take a left on 3rd Street, I take a right on King Street, and follow along the water. After I pass the ferry building, I take a left. So you can see with this system, you don't have to appreciate the relationship between these locations in three-dimensional space. You just need to know when you get to the ferry building, you take a left. This type of system is very efficient when you've navigated along the same route so many times that it becomes routine. But let's say you're going to work on the same route that you take every day, and there's a detour. Well, your egocentric system isn't going to work anymore, and you need to pull up your allocentric cognitive map to come up with another way to get home. So this system, this habit learning system, relies critically on the caudate nucleus, which is a structure in the basal ganglia deep inside your brain. The reason we know so much about the neural circuits important for navigation learning is because if you want to know how a rodent's cognition is working, you put them in a maze and you see if they can find their way out or get some food. So when people are looking at rodent models of Alzheimer's disease, for example, they evaluate how well the treatment's working by seeing how well the rodents can find their way out of a maze. So this is the most popular cognitive test for rodents. It's the Morris Water Maze. On this task, the mouse is put into a cloudy, cold pool, and the mouse is swimming around trying to find the hidden submerged platform so he can escape. He does this over many trials, and the platform is always hidden in the same place. However, the rodent starts from a different position on every trial. So the only way to get better and better at finding that hidden platform, which he's sitting on right now, is to learn the relationship between the hidden platform and the cues that surround the pool. in three-dimensional space, just like you know the relationship between Coit Tower and the Golden Gate Bridge in UCSF when you pull up a map of San Francisco in your mind. So we've developed some virtual reality tests of those two navigation strategies that we're using in our lab because we think that they're sensitive to different brain circuits and are disrupted by different diseases. So I'll show you a couple examples of these. So this is the human version of the test I just showed you. And we actually have a version of this test outside, and I invite you to try it after the talks. So on this test, you drive around in a circular field looking for the buried treasure. When you drive over it, it will appear. So you have many trials to find it, and for you to get faster and faster at finding it, you need to appreciate the relationship between the external cues, the houses and water tower, mountains and so forth, and the location of the buried treasure. Just like the mouse had to learn where the hidden platform was relative to the cues around the pool. So we think this test is very sensitive to hippocampal system dysfunction. And we're finding that it's particularly impaired in the earliest stages of Alzheimer's disease, which targets that system. I'm going to show you now another test that we're using, this one to measure specifically the egocentric navigation strategy. On this test, the subject navigates through a long route through a neighborhood. It's always the same route, and you learn it by trial and error. Each time you get to an intersection, you take a guess about which way you think it goes, and if you get it wrong, you're prompted to guess again until you get it right. Over time, subjects get much more accurate at this test, and it becomes almost a habit for them. So to do this test well, you just have to chain responses with local cues. When I get to this cactus, I turn right, for example. So we think these two types of navigation memory are really tapping different brain circuits in our brains, and that they're affected by different diseases. And I think we all use both of these strategies, but I think some of us tend to use one more than the other. So think to yourself, which strategy do you tend to use? There are actually some sex differences on these tasks as well, and men tend to be a little bit better on average on the allocentric navigation paradigm. Although I've definitely had some women volunteers who have done amazingly well. And one explanation for this comes from evolutionary psychology. If you think about hunters back in prehistoric days, they had to wander long distances through winding paths to try to search for prey and find their way home. They really needed to rely on that allocentric memory system. So I'm going to finish now with some take-home points. There are several types of memory. We've focused on the distinction between working memory and long-term consolidation, as well as the distinction between allocentric and egocentric navigation memory. Each type of memory relies on a set of brain regions and circuits. By measuring the function of different types of memory, neuropsychologists can make inferences about the integrity of the different underlying brain circuits. Why is this important? Why do we need to understand the links between memory and brain circuits? Well, memory disorders tend to target specific circuits. And so to treat these diseases, we need to understand how these memory systems work and why they fail. Also, even healthy people can benefit from these understandings. They can maximize their memories by understanding how memory systems work. Thank you.
All right, good evening, everyone. As Kate mentioned, my name is Bettcher, and I also often introduce myself to patients by saying that it's like the cheese, and feel very fortunate that I wasn't named after Gouda. So I'm going to be talking to you tonight about something I think is really salient to all of us, which is forestalling cognitive decline, so preventing any decline over time in our thinking. All right, so just to begin, I think one of the main questions that dominates our field is how do we slow the cognitive aging process? And by cognitive aging, what I mean is this typically gradual decline in our ability to process and manipulate information quickly. And this isn't restricted to middle or older age. We actually start to experience declines in how quickly we process things pretty early, even after our 20s. And so in terms of the research landscape, I think what has been most remarkable in the past few years is a transition in focus. So for quite a while, we've had an anchor in looking at preventing dementia, and this still is a very important focus of our work. But over the years, particularly the last decade, there's been even more focus on staving off decline, so not even necessarily dementia, but just preventing any cognitive decline. And in addition to that, I think in the last couple of years, we've seen a lot more information, a lot more media buzz around remaining cognitively robust throughout our life, and maybe even improving our cognition. I think this Newsweek article actually sort of personifies this interest that's developed over the past few years of how do we maintain our abilities and can we even get smarter over time. So transitioning from Dr. Possin's talk on spatial cognition and verbal memory, I plan to talk a little bit tonight about cognitive plasticity and brain games. And I'm also going to follow it up with a brief discussion of physical exercise. So how physical activity is related to brain health and what are the mechanisms by which physical exercise might actually impact our thinking. So just to provide some context for how this evolution in aging research has transpired, I think it's really important to examine early studies of plasticity and cognitive reserve. I think one of really the most striking examples of this comes from the early nun studies, which I think some of you might be probably familiar with. We talked about a little bit last year. The nun study refers to this longitudinal study of Catholic sisters. They were members of the School Sisters of Notre Dame congregation. There's actually a book on this topic. And this included approximately, it was a little bit over 650, between 650 and 700 Catholic centers were enrolled, and their ages ranged from 75 to 102 years old when the study began in 1991. And what was great about this study is that the sisters received annual examinations, and they all agreed to donate their brains upon autopsy. Donate their brains for autopsy upon death. Probably an important distinction there. So the nun study provided this really controlled means of evaluating predictors of cognitive resilience and also cognitive decline in a group of individuals who clearly had very similar lifestyles. So we didn't have to worry about any multiple partners across the lifespan, any exposure to particular diseases. It's a pretty clean sample that they had to look at. And from this study, the researchers led by Dr. Snowden at the University of Kentucky reported several important findings that I think has really changed how we think about cognition over the lifetime. And one of these findings includes the observation that some nuns had brains that were riddled with Alzheimer's disease pathology, but did not show any manifestations of a dementia. And Dr. Snowden reported several case examples, so including one of Sister Mathia shown there to illustrate the individual differences he noted in pathology and clinical manifestation. So Sister Mathia reportedly died at 104 years of age, relatively healthy, dementia-free, and upon autopsy, they noted that the severity of Alzheimer's disease pathology in her brain was at around a stage 4, suggesting that there was moderate spread of the disease in her brain, including the areas that Dr. Possin mentioned that are very important for memory, namely your hippocampus. So, stemming from this research is the question of how there can be such heterogeneity in clinical outcome among individuals who have a pretty similar degree of pathology in their brain. So importantly, I think it's an important fact to highlight that what we see under a microscope does not always reflect what we see in everyday life. It's not necessarily a one-to-one correspondence. So when you examine individuals with the same severity of Alzheimer's disease in their brain, some may show Alzheimer's disease related dementia, and some may be clinically normal with no dementia. And so the question really is, why is this? And how can we tip the scales towards clinically normal with no dementia? All right. And one theory that has led to an influx of research on cognitive exercise and training is the theory of cognitive reserve. And cognitive reserve was propagated by Dr. Yakov Stern. He's at Columbia University. And he developed this idea to account for the disparity between the degree of pathology someone has in their brain and their clinical presentation. So what is cognitive reserve? It really relies on the idea that there are individual differences in how tasks are processed that permit some people to cope better than others with brain changes, brain pathology, damage, or degeneration. So in the face of aging, or even Alzheimer's disease pathology, a brain with higher cognitive reserve may try to cope with impending changes by using pre-existing cognitive strategies more efficiently, or they may flexibly use different strategies for the same task. So cognitive reserve is really hard to measure because in many ways it's a theoretical construct, so we can't measure it the same way that we measure plaques and tangles in the brain. Because of that, researchers often rely on proxy measures to assess cognitive reserve. So this would be something like educational attainment, how far you went in school, your occupation, your mental activities, which is sort of a nebulous term, and your IQ. So consistent with what we saw in the Nun study, this also suggests that individuals with more cognitive reserve may be able to tolerate or handle greater amounts of damage to the brain before clinical impairment is evident. So I think the figure here illustrates this model nicely as it shows that at the same level of brain pathology, individuals with higher cognitive reserve are performing much better on the same tasks. So an alternative way to look at this is that individuals with higher cognitive reserve only start to approximate the lower levels of performance when they have more pathology in their brains. And there's been a tremendous amount of support for the benefits of high cognitive reserve. And I think what's nice about this conceptualization is that it's an active model. So it doesn't assume that you need a certain amount of change to your brain before you start to show difficulties in everyday life. And instead it focuses on the processes that actually allow individuals to experience these changes and still maintain a similar level of function. What's also helpful, I think, about the recent data is that even late-stage interventions to improve cognitive reserve look promising. So that could ultimately delay or even prevent dementia. And this is, I think, really intimately related to that concept of plasticity, which really relates to the brain's ability to modify its structure and its function in light of new experiences that we have. All right, and I think a natural extension of this topic is that of cognitive exercise and brain games. So translating the cognitive reserve and plasticity research into interventions has been kind of a difficult process, I would say. And there's an extensive scientific literature that is messy and difficult to interpret. So brain games, Sudoku, and intellectual engagement have been heavily fed to the media as this sort of ultimate panacea for cognitive decline. I'm sure most people here have seen these in the mainstream media before. And I should say that some of this has occurred without research supporting it. So what do we know about these things? There's been some encouraging results in terms of leisure activities that were reported in the last couple of years. And they've shown that people who have high rates of intellectual leisure activity, which they define as things like reading books, going out to operas, playing games at home, playing cards, taking a new class, that all of these were protective, and that individuals who did this had cognitive decline that started much later in life than individuals who did not report doing these activities. And so we're still a little unclear about the mechanisms by how this works, but there has been some promising evidence to suggest that even intellectually leisure activities might be helpful. Similarly, there's been a lot of buzz, and rightfully so, about cognitive interventions. These findings have also been mixed, and with some studies demonstrating a lot of benefit, and then some studies showing absolutely no benefit. And I think this is where being an educated consumer is critically important, particularly given the sheer volume of brain games that are being marketed to the mainstream public. So on one hand, we have studies that have shown no benefit from brain games. And by no benefit, I mean that when individuals are trained on these tasks, they do get better on these tasks, but that it's not generalizing to other things, to other important activities in someone's life. So for example, in a study reported in Nature back in 2010, researchers randomly assigned over 4,000 people to 2 different experimental groups where they were being trained on things like memory tasks or reasoning tasks, and then a control group. And they completed training sessions over a period of 6 weeks. And while, again, like I said, they show significant improvement in the tasks that they trained on, they did not show any transfer of benefit from that. And that's really what you want. You really want to have transfer of benefit to other things in your life for these to be most meaningful. So that's one side of the coin. I think on the other side, what we're seeing is in the last couple of years, there have been very encouraging studies that have been coming out. And I think what's different about them is that they are training people on very targeted cognitive processes. So they're very specific about what they're training the individual on. And it seems like that's probably most important in terms of reaping the cognitive benefits. So the findings are promising but mixed. And on the positive side, I want to give you an example from some studies that are occurring at UCSF. And these are going to be talked about a little bit later in the interactive portion of the night. So this is Dr. Adam Gazzaley's lab, and Dr. Angara, who also works with him and has really spearheaded some of these studies, will be here in the interactive portion to talk with you about these. So for these studies, the Gazzaley lab, in collaboration with colleagues at LucasArts, they have developed this game called NeuroRacer. And as you can see here, it's I think it even just looks really exciting when you see it. So this is really thinking about cognitive training in the context of single task versus multitasking. And I think multitasking is something that comes up a lot for people, something that can be difficult over time. So in this study, they are doing some pre-testing where they have people come in and they do some tests on them, and then they have people go home with these laptops and they do trainings at home on this task. And then they come back in later and do some more testing in the laboratory. So, and these tests are really designed to emulate multitasking in everyday life while controlling for specific cognitive processes. And so you can see here what we have is there's a single task version and there's a multitask. And with the single task, what they have is a sign that the participant will have to respond to. While in the multitask, they will still have to respond to that, but they're also driving a car. And so again, to really emulate the kinds of things that we're dealing with on an everyday basis. And from this, they calculate a multitasking cost. So what is the cost to your performance just by multitasking? And it's a fairly basic calculation that they use there. So using the index shown before, you can see the cost of multitasking increases across the lifespan. So in other words, the ability to efficiently handle and respond to multiple sources of information worsens over an individual's life. And you can see that this actually starts even in your 20s. Now, these results start to look very different upon providing multitasking training. So specifically, individuals who did not receive any training remained at around the same level a month later. Individuals who obtained the single task training at home, so again, they were trained on just responding to those signs without actually driving the car. Their performance, it looks a little bit better. This is not statistically significant. And then those who were trained on the multitasking component, you see this striking difference and a striking improvement in terms of how much cost there is there. And most importantly, what we see is that these actually hold over time. And so after a period of about 6 months, you're still seeing much better improvement with the individuals that were trained on the multitasking component. So again, Dr. Angara will be demonstrating this latest version of these games on an iPad during the interactive portion of the night. All right. Okay, so just to briefly review the cognitive engagement and brain game section of this, just want to say that in terms of plasticity and cognitive reserve, I think there's really strong evidence that our brains continue to change and adapt. That's part of what plasticity is. And research, I think, has really uncovered a lot of protective and risk factors for this. And in terms of the actual brain games, I think, as I said, there's a lot of new research suggesting that if it's targeting specific cognitive processes, that's the most helpful. And this is, I think, a really promising area of research, but also requires a critical eye and thinking about the fact that not all of these studies have a lot of research behind them. So being an educated consumer about this, I think, is one of the most important facets of it. So something that I am increasingly excited about is the role of physical exercise in brain health, and in particular how exercising might actually improve cognition and potentially delay or even prevent dementia. So what have studies shown? In general, what we've shown is that what's good for your heart is good for your brain. So individuals who participate in physical activity, particularly aerobic activity, they've shown in various studies that you can have up to 30% reduction in the risk of cognitive decline and dementia, which I think is a very striking and exciting finding because it's something that we can do something about at any stage. And in particular, just to answer that question, Christine Yaffe and Dr. Middleton at both UCSF and the San Francisco VA have conducted studies trying to answer the question, does it matter when you become physically active? So is it too late to start? If I wasn't doing any sort of activity as a teenager, is it too late to start in middle or late life? So what they found was that women who reported that they had been physically active, particularly during their teenage years, showed the lowest likelihood of cognitive impairment. So they seemed to be the most protected. However, individuals who became active later in life also showed a reduced risk of developing cognitive impairment. So even though it seems like a lifetime of physical activity is most helpful, people are reaping benefits from this even if they start late in life to become physically active. So it seems to be a really critical component to brain health. So in addition, that was more of what we call an epidemiological study on cognitive decline. So what if we turn our attention to what the brain looks like in those who are physically active? So research with animal models has shown that a molecule in the brain called brain-derived neurotrophic factor, or BDNF, is critical for neuron health and is really important for plasticity of our synapses. And exercise has been shown to have a really robust effect on BDNF levels in the brain. So in this case, if you have rats run on a wheel for as little as a week, what you can see is that they have nearly a 1.5-fold increase in BDNF expression in their hippocampus. And these effects were also still noted, so they were still raised 3 months later in these animals. And so you can see here that there's this induction of BDNF in various parts of the hippocampus. So that's the dentate gyrus. This is the CA3 and CA1 regions. If we kind of try to take that literature from animals and apply it to humans, we're also starting to see some really exciting results. And this study came out in the last year. And this was looking at 120 adults who were randomized to either a walking group or a stretching toning group. And these groups were completely identical, except that the walking group participated in moderate intensity walking for about 30 to 45 minutes per day, 3 times per week. So both groups received the same amount of social interaction and health instruction, so they really controlled for a lot of variables here. And then brain MRI scans were conducted before randomization, after 6 months, and again after the completion of the 1-year trial. So if you can see here that what they were really focusing on was the hippocampus. Hippocampus is a very metabolically active area that seems to be very sensitive to plasticity and where there's been probably the most research in terms of plasticity. So that's where they were really focusing on. The caudate and the thalamus were also regions that they looked at more for control areas. So with the hippocampus, what they noted was that for the individuals that were in the stretching toning group, they had about a 1.5% decline in their hippocampal volume over the 1 year. And this is very consistent with normal aging research. So this is something that we often see when we're following adults over time. But in contrast, what they found was that individuals who were in this more aerobically active group, that they actually had a 2% increase in the size of the hippocampus, particularly the anterior part of the hippocampus, over 1 year. And this was a significant difference in the two. So this is one of one of the first studies to really robustly show this in a regimented way. So these observational studies, along with others, provide considerable support for the hypothesis that physical activity may reduce the risk of cognitive decline in dementia. But how does this actually happen? And I think this is an important question to ask anytime we're reading literature about something new, is what is the possible mechanism behind this? How could this possibly happen? How does this confer benefit? And as you might guess, physical activity is related to lower rates of obesity. Like I mentioned before, what's good for your heart is good for your brain. So obesity, particularly middle age, has been shown to associate significantly with dementia in later life. Physical activity is also linked to reduced vascular risk. So again, anything having to do with your cardiovascular system, blood being innervated up to your brain, it has significant benefit for any sort of vascular risk factors that someone might have. So this could be diabetes, hypertension, cardiovascular disease. And as I had just mentioned before, it also seems to induce BDNF, which is incredibly important for neuronal function. And something that's more near and dear to my heart is its relationship to inflammation, which is something that I study in healthy older adults. And people who are very physically active seem to have lower levels of inflammation in their bodies. And inflammation has been shown to be related to your brain structure. In particular, what we have shown is that inflammation, people who have higher levels of inflammation, so they're just healthy people who do not have cognitive impairment, but if they have higher levels of inflammation, they seem to have lower integrity in the white matter areas of the brain. And so if you can see here, actually the white parts here and the green tracks, these are not clearly what your tracks look like, but they are color coded here, and you actually have lower integrity in something particularly called the corpus callosum that connects the two hemispheres of your brain together. And this seems to be highly related to inflammation. So people who are physically active seem to have lower levels of inflammation. So in terms of lower integrity, we use something called diffusion tensor imaging, which basically looks to see how well does water molecules move across a tract. And if something is really intact, like if you think about if you think about a fiber or anything that's a really intact tract, things should move along it very easily. If it's starting to degrade at all, you'll have lower directionality of the water. You can think about water just starting to spread out. And so that's how we measure that. So it seems like it's unclear exactly what's degrading necessarily, if it's the outer sheath of it, but it seems like there's lower, the structure of it doesn't seem to be quite as intact as it was before. These white matter tracts are really important for processing information quickly. So they connect all these different parts in your brain, the gray areas, they connect these so that you can think more efficiently. All right, and so just to start to conclude a little bit, what I want to really highlight here is that based on this evidence with physical activity, I think it's pretty clear that there's considerable evidence that you can reap the benefits of physical exercise at any age. And it's actually what we tell our patients the most often, I would say, in our clinics, is that this is something that you can do at any point in time, and it will really benefit your neuronal health, as well as benefiting cardiovascular health. And I think there's also ample evidence to suggest that exercise really reduces vascular risk factors, obesity, inflammatory markers, and may alter brain structure as well. So I think the combination of this cognitive training, cognitive exercise, and thinking about physical exercise are two very tightly interwoven facets of how we can improve our cognitive health over time and hopefully stave off dementia. All right, so I just want to thank my colleagues, and I really appreciate everyone's attention and letting me talk to you about this topic. And I really look forward to speaking with you afterwards in the atrium there.
So moving in a slightly different direction. My name is Winston Chiong. I'm a neurologist and neuroscientist at the Memory and Aging Center. And I bring a sort of an interdisciplinary perspective in that my PhD was actually in philosophy. And one of my areas of interest is actually in kind of points of contact between philosophy and other kind of more humanistic disciplines and clinical medicine and neuroscience. And so what I'll be talking about today is a little bit more speculative, but I'm really trying to take a look at some points of contact, some recent findings in neuroscience, and how we might use these in connection with some older ideas to think a little bit more about what makes us kind of uniquely human and kind of what contributes to our sense of self. And so hope you'll bear with me on that. So before I talked about the self, though, I wanted to start by talking about kind of a more general principle, which is the idea that brain diseases tell us about how the healthy brain is organized. That when we pay attention to what goes wrong when something happens in the brain, that gives us important clues about how things are connected in normal function. And one of my favorite examples of this actually comes from this passage from the Bible, which many of you will already be familiar with. But after tonight, I hope after you leave, you'll think about it in a slightly different way. So this is Psalm 137 from the King James Version, and this is after the conquest of Jerusalem by the Babylonians. And what's interesting about the psalm is that it describes two kind of divine punishments that the speaker would wish upon himself if he were to forget about Jerusalem. And the two punishments are, let my right hand forget her cunning, and let my tongue cleave to the roof of my mouth. And so if you think about this, either of these in its own right would be a very severe punishment, right? So for the first one, we're talking about essentially losing the use of the hand that 90% of us use to do pretty much everything, and we're talking about the loss of the ability to speak. And so you might think originally, well, this seems like a bit much, right? Like, why should it be both? Why should they happen at the same time? But I think that what's very striking as a neurologist when you read this is actually that these two problems often come together. We actually do tend to see people with both of these problems at the same time, and I'm assuming that the ancient Israelites observed this also. So to understand why, it helps to take a look at the brain. So this is a picture of the brain from the left side. So if you're looking at my left ear, if you could see through my skull, this is what you'd see. And I wanted to call your attention to a couple brain regions. So this region here in yellow is what we might call a motor speech area. And among other things that's done by this area is basically it helps us go from words to the actual movements that you have to make, again, with your lips, your tongue, and so forth. And one thing that we don't think about, because we're all fluent speakers of a language, is what a skillful and coordinated action it is to speak. Because basically you're talking about coordinating the movements, again, of your jaw, your lips, your tongue, your vocal cords, your breathing to produce each word. And ordinarily, you don't have to think about how to do that, and that's partly because the sort of motor program for how to perform all of those actions correctly is kind of stored on the left side in this sort of yellow region. Then close by, along this red strip, there's another region. So you may know that the left side of the brain controls the right side of the body, the right side of the brain controls the left side of the body. And so along this red strip is a region that controls basically the movements of the right hand. So the neurons in this region send signals down to the spinal cord that in turn send other signals down to the hand and basically control those movements. And so you can imagine that if something happens to the brain here, that it's likely also to affect this region and vice versa. And in fact, if you take a look at the map of the blood supply to the brain, there's a very important blood vessel that comes up through the neck, comes into the skull, and basically gives off this branch that supplies this whole region. So if something were to happen like a blood clot were to migrate or develop here, you can easily see how it would affect the blood supply to this region of brain. So this region of brain would be permanently injured, leading to loss of the ability to speak, as well as loss of the movement of the right hand. And it's sort of fitting, I think, to me that we talk about this as a divine punishment or in a theological context, because our English word stroke, which is the modern term we use for this disease when you have a blood clot that blocks this vessel, comes from the term the stroke of God's hand, right? So this expresses, again, the idea that this is a sudden, devastating loss of neurological function. And while the ancient Israelites probably did not know that this is the way things were connected, we can learn from this observation that has been made for a long period of time that this is how these parts of the brain are connected. So that's just an illustration that I like about how we can learn from these brain diseases about how these things come together. even if we didn't know about the brain itself. So this is a way we've learned about a lot about how particular parts of the brain work. We take what we call these focal lesions, these diseases that affect particular parts of the brain, so strokes, tumors. Dr. Possin talked about side effects of brain surgery. And so we've learned in this way about how these particular parts of the brain are important for functions like vision, language, memory, our control over movement, our sense of touch, and so forth. What is kind of a new frontier, though, in neuroscience, and this is what I want to talk to you about today, is a little bit more distributed in the brain, right? And that's the question about how do these parts all work together, right? How are these different functions brought together to make us who we are? Because we're not just language, we're not just vision, we're all of these things brought together. And the suggestion I'm going to try to present today is the idea that it's really the coordinated activity of multiple parts of the brain working together, and there's something we can really learn about how the brain is organized kind of in this way. So here we're getting, again, from sort of more hard clinical neuroscience to something that's a little bit more ineffable, a little bit more intellectual and philosophical maybe, and starting to talk about, again, the topic for tonight, which is kind of neuroscience and the self. And I think one of the problems that we have as a starting point is just the observation that when we talk about the self, people use this language in a lot of different ways and seem to refer to many different things that might be related, but it's helpful to think about these differences. And so one thing that philosophers like to do is to kind of catalog the ways that people use natural language. And so if we think about different ways that people speak about their selves, we can identify maybe hopefully a few themes. So obviously the self, the idea of the self, is very related to ideas of individuality, right? So myself, yourself, and also this difference between self and others, right? That there's a sort of boundary where I end and the rest of the world begins. We also see this, in immunology when we talk about, our immune systems recognizing self versus other. Another step that's related to this is the idea of reflexivity or reflectiveness, that we think about self-awareness, our ability to take ourselves as kind of the object of our thought or perception. And then there's a lot of ethical ideas, right? So there's an idea of personhood, that there's something special about beings that are selves, that have a self. There's a relationship to identity, and this is the problem that kind of most philosophers would think about in terms of the problem of self. And that's kind of almost the problem of what makes you the same person over time, right? So you're you today, and there's also you 5 days ago or 5 years ago, and what's the connection between them that makes it all a continuous shared life, a shared self. And finally, there's this ethical idea of autonomy, which again we go back to the Greek roots, is really giving a law to yourself, being the kind of being that can self-legislate in this way. And so what I'm going to suggest today, when I try to translate this language into sort of more the language of neuroscience, is that these different senses are related to, again, more global processes, not things that one particular part of the brain does, but rather these more general processes that integrate the activity of these different parts of the brain. So if we take again our lesson that brain diseases tell us about how the brain is organized, then one thing that we might look to for inspiration is to think about brain diseases that are not like strokes or tumors, but brain diseases that affect many different parts of the brain at the same time. And I'm going to get into a slightly controversial area, and I hope I don't get myself into too much trouble, but there is an idea that dementia is a disease that's very threatening to people's self. And I say it's controversial, so there are some people that say that this is something that happens. So here's a popular book for family members of patients with Alzheimer's disease, and the title of the book would suggest that, yes, this is something that happens, this is something we see that family members need to know about, that patients with Alzheimer's disease can lose their self in the course of the disease. But at the same time, you'll have other people who say, no, how could you say that, right? The self isn't lost in Alzheimer's disease, the self endures in Alzheimer's disease. And what I'm going to suggest in part is that some of this controversy reflects actually different neurobiological and neuroscientific aspects that are related to the self that might be preserved or might be lost in these different diseases. So hoping to broker a compromise of sorts in this. So I'm going to unfortunately introduce a little bit of philosophical jargon, but I hope it'll be helpful. Thinking about us as people, as agents that have to move around and be effective in the world and make sense of the world, there are two kinds of problems of sort of integration, right? So we talk already about the different functions that these different parts of our brain do. But they've got to be brought together in a coherent way that allows us to deal with the world and to be effective in the world. And two problems in particular that I want to focus on. The first I'll call a problem of synchronic unity. And by this I mean unification of kind of your activity at a given point in time. And the first observation to make is that at any point in time, there are hundreds of different things that are all competing for your attention, right? So you might be trying to pay attention to what I'm saying, but you might find your mind wandering to think about what kind of cheese they're going to be serving in the reception afterward, or, you know, how can I get my hands on one of those brain games? And in addition, there's also kind of sensory information, right? So you're listening to my voice, you're looking at the slides, but you might also be distracted by, you know, an itchy feeling on your leg, or the way the tag of your shirt is rubbing against your neck, things like that. And your brain is being bombarded by this information all the time, right? All of these things are actually being represented in your brain. These things, you know, are happening, but, you know, you can't be responding to all of those at the same time. And similarly, from the point of view of motivation, we all have conflicting aims and desires that can't all be satisfied at once, right? So you came here to learn about the brain, to learn about brain games and so forth, but, you know, you might have also hoped to go to a movie or meet some friends for dinner and so forth. And, you know, we know that we can't satisfy all these different aims and desires at once. And again, so in both cases, you've got to focus, you have to prioritize and allocate attention. And that's just, you know, in any given moment. Then in addition, there are problems that I'll call the problem of diachronic unity. And that's kind of being a coherent sense across times, right? Because, you know, your life extends far beyond this moment, far beyond this room. It extends forward and backward in time. And we all have important plans and projects that extend over the course of our lifetimes, or when we think about things, you know, for the sake of our children or important causes we actually have important projects and plans that extend beyond our own lifetimes, right? And so part of being human is kind of this ability to, you know, think about yourself extended beyond the present moment. You plan for the future, and then in order to do this, you've also got to be able to recall prior intentions, right? So you signed up for this course maybe a week or two ago, and then you had to remember today that today was the day you're going to come. You've also got to be able to keep track of different things that you do in order to realize these long-term goals. So yes, I already did step 1 and step 2, and then now I have to think about step 3 and step 4. And some psychologists have suggested that one way of thinking about this task that we all have as human beings is in terms of a faculty they call mental time travel, right? And so that's kind of the ability to project your perspective and, you know, to imagine yourself kind of in the future or in the past. And we use this when we recall old experiences, or when we think about, you know, particularly moving experiences that we had in life. But we also use it when we think about the future. So, you know, maybe you've never been to Barcelona before, but you'd like to go, and you can imagine yourself walking along Les Rambles or standing at the base of La Sagrada Familia and looking up at the spires, right? So it's helpful that I have two problems of the self, because there's also 2 different forms of dementia that I think might be relevant as disease models that tell us about the way that, you know, again, we think about the way the brain is organized in health, and we also think about the way that things can go wrong in the case of disease. And so one of them, Alzheimer's disease, is one that you've already heard a lot about. One that may be less familiar is this disease called frontotemporal dementia. I guess those of you who were here last week would have heard a lot about it as well. But, you know, these diseases tell us actually about different brain systems that seem to be involved, I would suggest, in these different aspects of self-integration, these different kinds of integrative problems of the self. So patients with frontotemporal dementia, these patients are very, very unique. They're very tragic in that they really have an inability to make their actions coherent, particularly, you know, just even in the moment. So these patients are often disinhibited. So these patients are prone to do things like, you know, they might see people in the supermarket, complete strangers, and say that they're fat, or that they would like to have sex with them. And, you know, one thing I would say is that, you know, these are thoughts that even in normal people might occur to somebody in the course of their interactions, you know, kind of being out in the world. But, you know, we know not to say these things. And sadly, these patients don't have that ability anymore. These patients can be very distractible, so even when they're focused on a particular goal, they can be easily distracted, and so they wind up doing something else. They have a certain loss of concern for other people, loss of empathy that might be connected more broadly to a loss of a sense of kind of the importance of other people. They tend to perform a lot of compulsive and repetitive movements. They might tap their leg in a certain way, or we've seen patients that rub their skin raw because they just have a tendency to rub in a certain way. Or they might make repetitive kind of vocalizations like in a certain way that can be kind of very inappropriate to the setting. They kind of overeat, so if there's food in front of them, they're likely to eat, especially sweets. Something I put in gray because it's not part of our formal criteria anymore, but it's something that we use clinically as a loss of insight. So these patients seem especially unable to reflect upon kind of the changes in their personality and the ways that their behaviors affect other people. So that's frontotemporal dementia. And then, we've also talked about Alzheimer's disease. And, two of the things that we've already talked about are, that they kind of forget these episodic memories. So they kind of lose the ability to lay down these memory traces and refer back to them. And as Dr. Possin pointed out, they also have trouble even in learning and acquiring these memories. These patients are often disoriented in time, so they lose track of the day of the week, the month, even the year. And they also have difficulties in navigation, right? So these patients don't get lost in time, but they get lost in space. So these patients tend to wander. They tend to lose track of where they are. So one of the things is that that's important to know about these diseases is that they don't just strike sort of randomly. They actually tend to occur in patterns. And they affect different parts of the brain, but they're quite repeatable in terms of which parts of the brain these particular diseases affect. And so here I have a map in blue. Might be familiar to those of you who were at Dr. Seeley's talk last week. But there's certain parts of the brain that are affected and certain parts that are spared in frontotemporal dementia, and similarly for Alzheimer's disease. And then what's quite interesting is that when we go back and look in the healthy brain, we've done a lot of research that looks at these sort of networks that are distributed across the brain. So again, not asking about what one particular part of the brain does on its own, but more research that's devoted to how these different parts of the brain are connected. And so we've identified these networks. When you look at them, there's a significant amount of correspondence between the areas of the brain that are affected, that are atrophied and lost in these dementia syndromes, and these networks that we see even in the healthy brain. And we're calling these the salience network and the default network. So I should say that while Alzheimer's disease affects the hippocampus, as was mentioned, there is actually this broader constellation of brain regions that's also affected in this disease. So for the salience network, when we look at this network that's affected in frontotemporal dementia, and we ask, what are we learning about what this network does in healthy people? We're finding that it's related to a lot of the functions that you might guess just based upon our knowledge of the disease. So we know that regions of this network are very important for things like value, what value we attach to things, even the value of things like money or relationships, emotion. There are nodes of this that are very closely associated with motivation and drive, with kind of the will to get up and do things. And then even very basic cognitive processes like paying attention and being alert or staying on task are all related to this network and are all very closely related to deficits that we see in patients with these diseases. On the other hand, we know from, again, studies of healthy people that this default network is important for things like autobiographical memory and envisioning the future. So these are things that we would relate again to this idea of mental time travel. A couple other things that the default network seems to be involved with that may be related. One has to do again with navigation, with certain kinds of tasks where we have to orient ourselves in space. The one that's also interesting is adopting other perspectives. So imagining myself in your shoes, knowing the things that you know, and which might be different from the things that I know. This seems to be involved. And also mind wandering, which might be actually tapping into some of the memory and envisioning the future, right? So when your mind wanders, you're often likely to think about maybe something that you're doing, a conversation you were having yesterday, or you might find your mind wandering to something that you'd like to do in the future. And kind of a broader picture that includes the idea of mental time travel that some people have proposed is that this default network is involved in engaging in these sort of dynamic simulations of possible states of affairs. So that, when we recall a memory, one thing that we do when we kind of reconstruct that experience is that we draw upon things that we've stored in the brain to recreate the experience that we had of that memory. And that we might use a very similar system when we think about something we're going to do in the future. So there we're not drawing upon memory per se, but we use a similar system along with information that we already know about some future event that allows us to simulate it in a similar way. So in conclusion, I've talked about two distributed networks, right? So again, we're moving beyond thinking about things that any particular region of the brain does in isolation, and instead thinking about what the coordinated activity of these distributed parts of the brain do together. And these networks seem to be very central to the activity of other parts of the brain. And I think that, when we think about what is the upshot of this for us, as human beings, that, the function of these networks seems to be to give some coherence to our thoughts, our motivations, and our actions. And my suggestion is that this problem that I've mentioned of synchronic unity, of kind of being a unified agent at a particular point in time, able to kind of deal with all of the potentially distracting information, the conflicting desires that we have, and so forth, is really something that is served by this salience network. And meanwhile, that this problem of diachronic unity, of being an agent that's extended over time, that's agency can go kind of back and forth beyond the present moment, is something that's served in part by this default network. And then getting back to the controversy that I mentioned before, if people were to ask the question, is the self lost in dementia, my suggestion would be that to answer this question, we really have to distinguish between different kinds of unity that are important to being a coherent, coordinated self. So I think that one thing that we definitely do see in Alzheimer's disease is a loss of unity, a loss of self across time, right? So these are patients who have trouble linking one moment to the next, and so it can be very, very difficult for these patients, to make plans or to rely upon their knowledge of past events and being effective in the present and future. But we also know that these patients can be very, very present in the moment. These patients can be very sensitive to other people's needs and emotions. They can respond in very socially appropriate, very graceful ways to all kinds of challenging situations. And this is, I think, what a lot of people refer to when they say that this is the preserved part of the self in Alzheimer's disease. Meanwhile, when we see patients with frontotemporal dementia, I think one of the things that's very striking about them is this loss of unity and coherence even at a given time. So just in a single interaction with one of these patients, you might find that they're distracted, that they're emotionally disengaged, they act in somewhat bizarre ways. But if they're paying attention, their memory of these past events and their ability to project forward and backward can be preserved. And so, so I think that overall, I'd say that when we think about these different diseases, we might think about different aspects, different tasks of kind of self-integration, and see ways that they can stay together or come apart. Okay, thanks.